A very good morning, my dear students. Welcome back. Let's continue the chapter called Alternating Current. I hope you could remember when this alternating current, just a minute, when this alternating current source is connected to a resistor, we had already discussed about it. What happens to the instantaneous current and what happens to the instantaneous EMF values. When this alternating current source is connected to an inductor, this point also we had learned what happens to the instantaneous EMF and instantaneous current. Now today's session is about when alternating current source is connected to a capacitor. When it is connected to a capacitor, what will happen to the induced current, which is instantaneous current and instantaneous EMF values, and that is our topic of interest now. And it's so easy. What we have learned in case of the first resistor condition, we understand some waveform and we also understood the topic called phase diagram. Not only in the case of resistor, in case of these two resistor and inductor case, we have drawn the waveform and we have drawn the phase diagrams even, right, between I and T or E and T. Now, let's start when AC source is connected to the capacitors. See how simple it is. Look at here. There is a capacitor which is connected to an AC source here. So this is the AC source voltage. You know the symbol of representing the AC source voltage. What happens? This is the source voltage. E is equal to E naught sine omega t. This you know already. So let's say the first cycle, there is a positive terminal and a negative terminal. At this particular instant, I'm talking about, my dear children. And slowly, as the current is passing through the circuit, what happens? The positive charges will be accumulated at this plate of the capacitor. Obviously, the negative charges will be accumulated because the negative end of the source is connected to this plate. Okay. And there is a potential difference will be developed across this. Okay. And this potential will obviously equal to the source potential. Okay. So in this case, what happens? V is equal to source potential. So that V is equal to E naught sine omega t, my dear students. Now, from here, when V is equal to E naught sine omega t, what is our aim? Our aim is to find, simple, our aim is to find the relation between I and E. Okay. So now from here, so what I can write, where V is equal to E naught into sine omega t, right? That is what I'm going to write here, somewhere here. So V is equal to E naught sine omega t. All right. Now, what is this V here? So from the case of capacitor, we know Q is equal to CV. From here, V is equal to Q by C. From here, what? V is equal to Q by C. So let us apply this here. So V is equal to Q by C, which is equal to E naught sine omega t. Okay, so this, let me write further. So Q is equal to C into epsilon naught sine omega t. So what is this Q? Q is instantaneous charge. At that instant, the charge on the capacitor. So you know the current. See, our aim is to find the relation between I and epsilon. I said, where epsilon value we already know, E naught sine omega t. Then I will be what? Instantaneous current. I will be what here? So this I can write it as dq by dt, my dear students. I is equal to what? dq by dt. So where I can say it is d by dt of q. Q is C E naught sine omega t. So from here I could write C and E naught are constant. D by dt of sine omega t is cos omega t into omega. Okay, cos omega t into omega. So here, so one more point I'm just going to write here. Listen carefully. Here, C omega epsilon naught cos omega t. This I can also write it as here. Let me write it here. I is equal to, what is that? Epsilon naught divided by 1 by omega c. No confusions, right? So this will be finally equal to epsilon naught into omega c only. Okay. So into cos omega t. So I is equal to, what I can write? I naught, because the complete expression I am naming it as I naught. Okay. So I naught into cos omega t, I can write it as sine omega t plus pi by 2. Can I write like this? Sin 90 plus theta will be cos theta only. Okay. So now I have got this expression. And you know already epsilon is equal to epsilon naught sine omega t, my dear students. So we have epsilon, that means instantaneous EMF and instantaneous current. Okay. So what are these two values? So these two values are called instantaneous EMF and instantaneous current. Is there any confusion? No confusion, right? Very good. So let us compare these two I and E values. I is I naught sine omega t plus pi by 2. So what is the phase difference here? Is there any phase difference here? Phase difference is pi by 2. Carefully see. There is a phase difference. So when there is phase difference, both the I and epsilon waveforms are not starting at the same point. 100% they're not starting at the same point. Okay. Now, and one more interesting thing I'll show you here. Look at this. There is a current, right? Sorry, just a minute. So this current I is leading, this current I is leading EMF by pi by 2. Yes or no? Because here I is equal to I naught into sine omega t plus pi by 2. Here E is equal to E naught sine omega t only. So current is leading. In the case of previous concept, what was our previous concept? Our previous concept was inductor. When AC source is connected to inductor, so let me write it somewhere here. Let me write it here. When this AC source was connected, this was the last topic, okay, connected to an inductor, what happens? Exactly reverse was happened. Here current is leading the EMF, right? So there current is lagging the EMF by pi by 2. Okay, clear? Just this was the previous concept. Let's come back here. So here current is leading the EMF by pi by 2, and let's draw the waveform first here. And before moving to the phasor diagram, let's draw the waveform here. Where is the waveform? So this is E or I. This is T. Carefully see. E I am drawing here. This is the waveform of E. Now, so this is the E naught, and the other side there will be minus E naught. Now, let me draw the graph for I. See here, I is starting from here. See, I is starting from here and moving like this. Okay. An interesting thing I'll show you. Carefully see the interesting thing. What does it mean? This is the I naught. Okay. So this is the I naught. So when E value is 0, instantaneous EMF is 0, instantaneous current is maximum. Okay. And when the current is 0, instantaneous EMF is maximum. In this way it goes. Right? Again, when instantaneous EMF is 0, and you see the current value at this point, it is the negative maximum minus I naught. So this is the graph waveform of E and T or I and T, right? When an AC source is connected to, when AC source is connected to what? When AC source is connected to the capacitor, no confusions. And let's concentrate on a phasor diagram also, my dear students, right? So phasor diagram, let's concentrate on the phasor diagram. So phasor diagram is so simple here. You can draw the phasor diagram in two ways. So here, if current is leading, that means if this is the current, this is the EMF. So current is leading because by an angle pi by 2, right? Phasor diagram we draw in anti-clockwise direction. If this is EMF, this must be the current. And another way of drawing the phasor diagram will be like this. If this is the EMF, then in anti-clockwise direction by an angle pi by 2, and you can see there is a current. That's it. That's called current is leading. Current is leading the EMF by pi by 2. So whereas in an inductor, current is lagging the EMF by pi by 2. Right? I hope there's no confusion at all for you till now. Okay. Now, let's see the one more important area I just wanted to concentrate here. So what is this I naught? See, what is the I naught value we had written already? So this is I naught, which is equal to epsilon naught by 1 by omega into C. Okay. So is it omega naught by resistance? Yes or no? Because current is equal to EMF by resistance. But in this circuit, resistance is not due to the resistor. Resistance is due to this capacitor. Yes or no? Resistance is due to this capacitor. So that is why this resistance is called as, see here, that is why this resistance is called as capacitive reactance. What is it called? Capacitive reactance. This resistance is called capacitive reactance. So sometimes the questions will be asked like this. This is also like 1 by omega value is 2 pi into frequency into capacitance. Okay. So this is equal to X suffix C. Okay. So capacitive reactance is denoted with the symbol X suffix C. So here, like what we discussed in the last class, so here capacitive reactance is inversely proportional to the frequency when C is constant. This capacitive reactance is inversely proportional to C when F is constant. So inversely proportional graphs, how it looks like also we know. So this is the graphs looks like of inversely proportional, right? No confusions. All right. So commonly the questions will be asked like this. So they give capacitance. For example, a given capacitance is 50 microfarad and its frequency is also will be given like 50 hertz, right? Commonly asked questions I'm telling you. So then they'll ask you to find the capacitive reactance. How simple it is, you see, 1 by 2 into 3.14 into frequency is 50 into capacitance is what, 50 into 10 raised to minus 6 farad, because it is 50 micro. Okay, so you can find capacitive reactance value will be almost 64 ohm. So what do you understand? So these dimensions of this are the units of this are equal to the resistance units, or resistance dimensions, right? Because this complete expression is representing the resistance. So you know the SI unit of resistance is ohm, right? What our SI unit of resistance is ohm. Okay, now so from here you can also find, if they give AC voltage is equal to 100 watt. What is AC voltage? It is equal to ERMS. ERMS is 100 volt. So now you know the value of IRMS. What is IRMS? IRMS is equal to ERMS by resistance in this circuit, that is called XC. This is 100 divided by, so this is 64. It is almost equal to 1.6 ampere, my dear students. So in this way, questions will be asked. So it's 1.6 ampere, my dear. Clear? Like these questions will be asked. Now, here itself, we know the instantaneous power, my dear students. Instantaneous power, which is equal to instantaneous EMF into current. Instantaneous EMF is E naught sine omega t into instantaneous current is what? I naught sine omega t plus pi by 2. Okay, so this I can also write it as I naught into E naught, right? Sine omega t, see carefully, see, the sine omega t into sine 90 plus theta is cos theta. This is cos omega t. So the same thing I can also write it as E naught I naught divided by 2 into sine 2 omega t, because sine 2 theta is 2 sine theta cos theta from that formula. So this is instantaneous power. Okay, so now for full cycle, the average power also I can find. What is the formula for average power? Integral P dt divided by integral dt. So this is 0 to t and this is 0 to t. So if you integrate this expression, right? See, if you integrate this expression, you get the average power consumed by the capacitive circuit is 0. Same way, here also the average power, here also average power for the full cycle in inductive circuit is also 0. Whereas in resistive circuit it was not 0. What was the answer? Resistive circuit, it is I square RMS into R. So that is the average power consumed in this case, in case of resistor. But that is only the situation os is not equal to 0, but the power consumed in the inductive circuit average value is 0 for full cycle, and for full cycle average power consumed in case of capacitive circuit is also 0. Okay, clear? So this is how the concepts will be asked. Now in the next sessions, what we are going to do, my dear students, in a circuit, see, just pause your video and you can note down the things. And if possible, I may give you the PDF of this document even, right? So now let's continue. In the next sessions, what we are going to discuss is there is an inductor, there is a capacitor, there is a resistor. All right. So this is L, this is C, and this is R. So these three elements are connected to an alternating source. Okay. So in this case, if it is positive terminal, negative terminal, current value, right? So we know alternating EMF is same, E naught sine omega t only. Here also we will find the current, instantaneous current. This is instantaneous EMF. Okay. So in this case also we will be concentrating and learning how to draw the phasor diagrams here. So if the question need to be asked in this alternating current, most of the time there is a possibility of asking a question from LCR circuit, my dear students. What is that? LCR circuit. Okay. So the biggest topic, the huge topic of our interest in this chapter is this LCR circuit only. Okay. Now, that may be CR circuit, maybe LC circuit, maybe LR circuit. Whatever it may be, there is an opposition for the current in the circuit, right? So in AC circuit, whatever may be the element, there is an opposition. Yes or no? There is an opposition. You know, that opposition for the flow of current is called impedance. What is it called? Impedance. This impedance is denoted with the symbol Z. That impedance is also opposition. That is nothing but the resistance only. There's nothing but what? Resistance. SI unit is ohm. No confusion. Okay. That impedance is Z. So this impedance can be written as, generally resistance is I is equal to V by R. So resistance is V by I. So this resistance may be E naught by I naught, or this may be ERMS by IRMS, my dear students, right? E naught by I naught, which is equal to ERMS by IRMS. Remember this impedance, okay? So opposite to the impedance, that's called admittance. What is that? So that's called admittance. It is denoted with the symbol Y. So Y is equal to 1 by Z. Okay. So this is admittance. Admittance SI unit is opposite to the resistance. That's called ohm inverse, right? What is that? Ohm inverse R. So that is called MHO R seen. So that is almost similar to the conductance, my dear children. Okay. So in this way, this topic, a simple topic will be discussed. Now get ready for your assignment of 5 questions. So your today's assignment will be based on when AC source is connected to resistors, when AC source is connected to inductor, and AC source is connected to capacitor. These 3 things you need to revise because very less time it will take, and all 3 are similar concept, right? So the next topic is what? LCR circuit. We will start in the next session, my dear students, right? All the very best. Thank you so much.